Hey everyone, it's Greg back with another video on data science and machine learning, and today we are going to make a full-blown computer vision image classification project from start to end, explained for all beginners and intermediate people in deep learning. The process of how to make a project where you can take an image and it has some sort of image in it. We're going to do cats and dogs, so it has a cat or dog in it, and you can say, oh, this picture is either a cat or a dog. We're going to make an application that is able to do that and actually get a very high accuracy on a test set of information. The reason this is useful is two reasons. One, you need to understand the process of building the application, and two, you need to understand that it's very, very easy to change this project of something from learning cats and dogs to something of your own. Maybe something I came up with in my 21 project ideas was making an image classifier on different bread. So maybe you had something that could recognize rye versus white versus brown bread. I don't know. Maybe you can, maybe you can't. This is a really good project to spice up your resume, whether you are going full-blown into computer vision or you're just kind of using it as a way of learning deep learning, convolutional neural networks, and transfer learning are some of the topics we're going to talk about. If you're interested in learning those, then please watch to the end. If you are unable to watch to the end right now, press subscribe so that you can get it back easily and you can get all the other useful information that I'm giving out pretty much constantly. I'm trying to get a video every day, even a couple of videos a day sometimes. Final thing before I get into it is please check the video description if you're looking to learn anything about data science and machine learning. There's a lot of information from me and from other materials as well. Click subscribe before you run away. Let's get into it. All right, so don't let this scare you. This is me just walking over the code that we're going to write together. Don't worry, I'm not going to throw all of this code at you. This is just a highlight showing later what we're going to have built so that you know in general right now what we're going to do. It's all code right in the same notebook here, and a lot of it is actually just moving to the right file structure. So in Kaggle, it's all in some input directory, the photos that we need, the cats and dogs, and we are going to create our own kind of file structure to make that slightly easier. So that is all of this, all of this, all of this, and all of this. It looks crazy, but it's really just copying and pasting and writing a very simple function that moves files from one place to another on the machine so that we can easily work with it. There is going to be a bunch of Tensorflow imports. I know that even anybody gets freaked out when there's so many imports thrown at you all at once. We're going to go through one by one why we'd actually want each of these. And here are constants saying basically what our file structure is so that we can link that to the TensorFlow. We're going to make a convolutional neural network using transfer learning, and it's going to be very accurate. We're going to use what's known as the image data generator, which is basically a Keras thing saying, okay, here's our file structure, here's our pictures, iterate over it, give me the train, validation, and later test accuracy, as we'll see. And that's how we fit the model, is actually training it. And we're going to call model.fit as usual in Keras. And a very slight change to the model will be basically just adding in a pre-processing layer. It's something to do with the image data generator, and we're going to save the model. And that is it. Really, that is all the code. So if that doesn't freak you out, or if it does freak you out, don't let it freak you out. Seriously, it's going to be nice and easy. And we're just testing the model here. So after we do it, we have saved the model. We're going to load the model, which is simple as load model from file directory. We are going to use a test data generator, so an image generator that iterates over our test set, and it says it's going to help us see how well we do. We are going to write a very simple prediction function which outputs the label, and we're going to compare that to the true labels to obtain a final accuracy on the test set. All right, so again, if you haven't subscribed already and you plan on running away once we actually start writing code, we're about to start writing code right away. So if you're going to run away, subscribe first. Okay, sorry for the quick jump there. You'll have to navigate, which I'll link in the description. Take a look at that, to the cat and dog on Kaggle. So thank you, Schubert for dedicating this to the public domain. That means I can use it in a YouTube video, so thank you. And yeah, let's just go right into it. So you start by choosing Write New Notebook. That'll boot up a session on Kaggle. And for now, we don't need a GPU. You'll see, hopefully you can see this on the right. It says accelerator, and we don't have anything yet. You have a limit to how much GPU and TPU. I got an error when I tried, so don't worry about it. GPU is fast enough anyway. TPU should technically be faster, but doesn't matter. Right now, we don't need anything. We'll just use the CPU. But when we go to actually training the neural network, we are definitely going to switch to a GPU because it speeds it up like 100 times, something like that. It's very, very fast. So I will tell you that on my monitor to the right, which you can't see, I do have that other notebook so that sometimes I can reference it. You know, this video would be like 3 hours long if I had to go in and grab different information. So just letting you know, it's going to be quick and easy for me, but for you, if it takes a little longer because you don't have something like this to copy from, or maybe you do, maybe you are choosing to copy a little bit from me, which is totally fine. I'm just letting you know it's there. So the first thing, Kaggle does this by itself. We have a random notebook name and we have a bunch of stuff at the beginning to basically describe what Kaggle is and the environment that you're in. So firstly, I'm going to change this to a computer vision, cat and dog image classifier. Okay, not the best name, but it's fine. And I'm going to eliminate a lot of this stuff. We actually don't need any of this for now. We'll probably get NumPy back later. I don't think pandas, and we don't really need that. Okay, I can tell you what it's going to say. So just run this and you'll see what it's doing by the output. We don't really care about how it's actually being done just yet. It's also being a little bit slow because it's doing the initial session boot up thing. And also there's a lot of files. So after it, there we go. Okay, so you can see basically what it's doing is iterating over the specific files that we included. So I got this from the cat and dog thing. And so what it's showing us here is that cat and dog input. Now we have, it's all in Kaggle input, cat and dog. For some reason, test set /test set, there's no reason for that. And I'm going to kind of change that as we make this file structure to be what we want. I showed you earlier that we're going to make it into train, test, and val. Right now, it is actually only, I'm not sure if you can see on the top right, but basically we only have a test set and a training set. And you can see it right here. We have a bunch of test sets, or we have one test set, but a bunch of images in the test set. Sorry for hurting your eyes here. There's a lot. We have a training set, and yeah, so test set and training set. Basically, the file structure right now as is input, cat and dog, test set, or training set. So it's either test or training. And in each of those, we have cats and dogs. So it's training, cats and dogs, test, cats and dogs. And there's going to be about, I think, 4,000 if each in the training set and about 1,000 in the test set. We want to organize this into our own training test validation set. So that is the first thing we're going to do. Actually, right now, there's just a really easy thing we can do here, which is this. If I change it slightly, and you don't really need to worry about what I did, just see what it does, is that we have, I'm just showing 2 files from each folder, and that's a much easier way to basically see what I just said, is our file structure has test set dogs, test set dogs as well. There's a bunch of dogs here. Test set cats, training set dogs, training set cats. We want to change this into not Kaggle /input because that's read-only. We can't really touch that. We can copy from that, and we're going to. But the first thing we need to do is basically move all the stuff from input, this cat and dog training and test set, move that into /Kaggle /working because we can actually manipulate that file structure. It is right axis. We can mess with that. So we're going to copy stuff from this input into our Kaggle /working. Now, you're going to ask the question, at least you might, why aren't we just doing it in code, the way to basically in memory fake the fact that we have a validation set, as in use some like scikit-learn library or a Keras library to say that this is our validation set, even though on the file system, it is only, say, a test set. Well, the reason is actually just out of convenience, is I'm going to make the code really, really easy to write by using image data generators where we have one for training, one for test, one for validation. So you don't have to do what I'm doing, but it is a very easy way to do this. It's like called flow from directory, it's all the training stuff's in the training folder, all the validations in the validation, all the tests is in the test. And it's a very easy way to do that. Now, sorry for that taking a really long time talking about the folder structure. Sorry, we're not done. It's going to be a lot of setup to get that done, but it's so much easier after we do that to get actually going on the computer vision stuff. All right, so before we worry about moving any files over, let's just set up our folder structure as is, because I'm just going to quickly go into the console and I'll show you that it's kind of obnoxious when using the console in Kaggle because it always goes back to the cell for some reason. So I'm just going to close that for now and then basically write some simple commands. So where are we is pwd print working directory. We are in Kaggle/working. We can write to this folder. Now, if I write ls, that says what files are here. Well, I guess this is probably our notebook, and that's it. So we want to make a directory called data, so put all of our data in, and we also want to have one for model, so that's where we're saving our Keras model, TensorFlow Keras model. And so we're going to have data in this folder, we're going to have data, and we're going to have model. The data is going to have all the data stuff. So in data, it's going to be train, test, val, and in train, it'll have cats and dogs. In val, it'll have cats and dogs. Test, it'll have cats and dogs. But in model, it'll just be where we save our model. There's not much going on there. Okay, so I'm going to copy one thing from my code over here. It's very simple, which is just importing the OS library. I'm going to expand that again. Importing the OS library, and then call os.makeDirs /Kaggle/working/data. You could probably guess what this is doing, even if you have never seen it before. It's just saying, let's make the directory /Kaggle/working/data. All right, so by directory, I mean folder. So we can make that folder, but I'm not going to run this because I want to do it all in one go. And I am going to copy and paste here because it is just very simple stuff, and you'll see what I'm doing is I'm just wanting to run this whole cell once to set up our folder structure. This is making the folders. So to make the training, validation, and test set, we must first have created the data directory. So we do that, and then in that, we're going to make 3 more folders. So we have data, train, val, test. And then in each of these, we are going to have cats and dogs. So in train, we'll have cats and dogs. And then we're going to do that again for validation and test. I'm going to copy all those at once because I'm pretty sure that makes sense, is we're just making the data folder, train, val, test, and then in train, cats and dogs, in test, cats and dogs. So that's this, test, cats and dogs, validation, cats and dogs. I hope that's pretty clear. And then the only other thing is this final one here, which is /Kaggle/working/model. So above the data in working, we're going to store the model stuff. All right, so hopefully you can now again visualize the file structure that we're going to use. I am going to run this, and I don't ever want to touch it again because it's just making all of the folders exist. I'm not putting anything in them. These are just a bunch of empty folders so that we can move the stuff that we want to. Okay, so now we're done with creating the folder structure, but to actually move the files there, what we're going to do, the easiest thing, is to write a function that can move all the files from one folder to another. Now that function is mostly well written already. It's mostly a copy and paste from somebody else's code, but we want to write it so that we can just call something very easily, where we give it a source folder, which is where it's coming from. So a source folder would be basically up to here. So we would call this function with training set dogs to move into our training set dogs. We would call it again with training set, sorry, that's the same thing. With training set cats, we would move into our training set cats. And the only tricky thing is that we also want to write it so that we can move from the test set into a validation set, because we don't have a validation set existent already. That's the main reason we're doing this. And so the way to do this is, if we're splitting the data set, we can basically write this function that has an optional parameter that says, do you want the left, the right, or everything? Okay, so if we're doing it for the test set information, so if we're moving stuff from the test and we're moving that into test, then maybe we can say, let's take the left portion of that, and then let's give the remaining right portion to the validation. That way we have a split between them, and it's not any overlapping files. It's just half goes in the validation, half goes in the test set. All right, so how do we write this function? We're going to import shutil, which is for basically moving stuff around on a file system. Now we're going to write this function that we described as we need to take in some sort of folder. So it's saying, okay, where is this stuff coming from? Where is it going? So these are just going to be strings of this folder and this other folder. Move it to here. And we're also going to give it this half equals empty string for now. All right, so it's an optional parameter where we're going to write this so that if we haven't even touched half, so if we haven't used it at all, or if we haven't assigned it, as in we called it with just source and destination, then that means we want every file in there to be moved. And by the way, when I say move, we're actually copying because it is a read-only access from the source folder. Okay, so we're writing this so that from source, we are going to move either the full thing, all of the files in that folder to destination, or just the left, or just the right. And so we'll call it with either not touch this at all, or set half equal to the string of left, or set it equal to right. All right, so we're going to make this function. Now, the first thing we're going to do is basically get a list of all of the files in the source folder. Okay, so source file list, so as a list, is equal to os.list_dir, and then source. Okay, so given our source directory here, we want a folder that says, okay, here is all of the names of a file. And let me just show you what this does for now, which is we'll make it basically echo, or I'll make it return source file list. That is not the end goal, it's just what we're doing for now. If I move it with some sort of existent folder here, so I will give it this folder. All right, so give that. The second parameter we don't even care about right now, so I'll just set empty string. What this does, notice it's just giving the name of the file without the full extension. So that'll be very important for how we write this function. But it's saying, okay, here's a list of comma separated values. Well, that's what a list is, for all of the file names. All right, so what do we want to do from there? Well, now that we have a list of the files, we can write this if-else statement for what we want to do. Okay, so it's if our half is equal to left, well, then what do I want to do? Well, I'll just figure out for then. I want to basically change what's in source file list to just the left half. All right, so I'll worry about that code later. Otherwise, if half is equal to right, well, then I want to basically, I'll copy that comment there. I'll change what's in source file list to just the right half. All right, probably could have guessed that one. And there's no need for an else, because if it's not left and it's not right, that means we haven't touched it, or you're doing something stupid and something we're not going to do. If it's not left and right, or right, then we're happy with how it is. All right, so for f in source file list, okay, so we're going to iterate through all of the files that are in that list. We're just iterating through this thing. Then what do we want to do? Okay, well, we want to copy. And to do that, we're actually finally using our shutil, and it's going to be called just .copy. All right, so copy, and then the source plus the f is the whole path. Okay, so copy is basically just a Linux command, or it's translated to a Linux command that's saying, all right, move this from here to there. All right, so here is our source, which is the full path. So that's the source, which is the base folder, plus whatever the file name is. So that's why we're iterating through this thing. So for each of these actual full names, we're going to move that into dest. All right, that's it. And that is the whole function. Okay, that's really all it's doing. We just have to write this piece, which is change what's in the left or change what's in the right. And so how we would manipulate that is source file list is equal to itself. Now, if we want just the left half, then what we can do is up until the length of this thing over 2. Okay, so that's saying this gives the length of the whole thing, and then if you divide it by 2, that's the index of basically the middle point. And so the colon syntax is saying, I want the first all the way up until that middle point. So that'll give the left. And then you can very easily change this to the right half by doing this. So I just switch the place of the colon. And what that does is saying, okay, no, I want to start at this middle point here and then take everything to the end. So that's the right half. That's the whole function. I'm just going to give it a print. And actually, I'll just copy this because it's much easier just to show you what it does by reading it out and not typing the whole thing. So I'm printing the string of the length of the source file list. So that's how many things we actually moved, which is dependent on the initial folder structure, as well as whether we took half or not. So we took this many files, we copied it from source, wherever we came from, to the destination. All right, that's all it's doing. And now I don't want to test this thing. You could test this thing on another file structure, but the easiest thing to do is just get this code right the first time. If you are writing this code and are worried about it, then yes, absolutely check your own code without messing with the file structure, or just kind of restart the session if you're, or factory reset the session if you're messing up a little bit, because it's kind of tricky. But what we want to do, I'll just show you one of these things right now. Okay, actually, apparently I already did that move. No, sorry, that was from earlier, or I was testing it. Okay, so I just copied and pasted something there. So what I want to do is moving from to this. So for training set / dogs, we want to move all the stuff from training set dogs into that existent folder structure that we created, which is now right now empty. So we're moving all of the training set dogs into our train / dogs. That is right, because we don't want to touch the half thing, because for training, we want to move all of the training over. And so for cats, it is as simple as changing that to that. All right, so we've moved all of the training set. After we call this, we'll have moved all of the training set over. Now, let me show you one of these, which is for the tests. So from test, we have test set / test set, moving that from dogs into our test / dogs. Okay, and we want to do that, but only we'll choose the left half. All right, so that means for the validation, we'll move the right half. All right, so then the easiest thing to do, to show you here, is just if we're moving cats in test, let's move all the cats to the left. And then the validation, let me copy one over here, just so it's nice and easy, is we have test set, not test set. Sorry, that's the wrong one, my bad. If we take it from, no, that's not the wrong one. I confused myself, because we are moving from the same folder structure. So we have test set / test set / dogs, and we are moving to data / validation / dogs. Remember, we created that folder, and then half is equal to right. So if half is right, then we're taking the other half, and we'll do the same thing for cats. Half is right, and that is good to go. Right? Okay. So basically, we're moving all of the training set into this our training set. We're moving the left half of the test into our test, and we are moving the right half of test into validation. And after we call this, it'll take a little bit of time, and it's going to output what it's doing. And we should actually read it, because it's kind of important to know how many files we actually have here. And once that's done, I'll get back to you. Okay, it's done, and you should know it's done because we have 6 calls, so we should have 6 different movements. So we moved 4006 dogs into training dogs into dogs, training dogs, that's funny. 4001 training cats into our training cats, 506 for each of the test dogs and cats into our test, and 507 and 506 into dogs and cats into our validation. That is close enough to perfectly balanced. That's fine. I know that was kind of irritating, because the first thing we do is set up a file system, and we're not doing any computer vision, but that's how these things go. And now it is set up so that we can very easily do this work, and we don't have to worry about that later. It's all figured out, and we can write the code so that it works really, really well with the file system that we now have. Okay, so that we can quickly and easily use this file structure that we have, I'm just going to create constants that have all of the files that we need in a variable, and I'm really just going to copy that, because it is nothing more than writing constants to where we are. So from OS, import path is just a very easy way to connect path-based strings. And so we have data path is equal to kaggle /working/data. That's where our data is. And then the train directory is the data path joined to the train. So it's basically just data path /train, which means kaggle working data /train. And we have that for validation, tests, and for model, we have just this string here of working model. So we have all those in a constant so that we can refer to those below. For the computer vision stuff, it is going to be a middle difficulty conversation as to what's going on here. It's very little code and effort to write after you understand what's going on. So I'm just going to explain for a second sort of what transfer learning is if you don't already. If you know what it is, then just skip over the next minute or so. But basically what we are going to do is an existing convolutional neural network, I have a really difficult time saying that word every time. An existing convolutional neural network, such as VGG or exception, you may have heard of these, we are going to use exception, is basically a huge, very long convolutional neural network whose job is to take an image, and it has been trained on, say, ImageNet, which is a data set with 1,000 different classes. So our job is to translate an image into either, its output is either a cat or a dog, and so there's 2 classes, but an existing one has, say, 1,000. So we are going to use transfer learning, which basically means, okay, you know that whole many layers up until the end where we have a softmax layer, which is a vector of probabilities that is saying, okay, what's the probability of class 1? What's the probability of it being class 2? What's the probability of it being class 1,000? Okay, so that's a whole vector at the end that adds up to 1. That's what the neural network is outputting. We want something very similar. We want something that still takes an image and outputs what class it is, or the probability of each class, except we want to translate this into just 2 classes. So what we do with transfer learning is that we take off the last layer, say, okay, no, we don't want 1,000, we want just 2. All right, so I'm going to do that with code very easily. I'm just going to copy this and paste to show you what it's doing. All right, so we're going to use exception, as I said. So we're going to, from Tensorflow.Keras.Applications, import exception. And so we create the base model, which is just exception, and freeze its layers for transfer learning. Okay, so meaning we take exception, which is going to have an input shape of a picture, which is going to be, say, 299 by 299 by 3. The 3 is because it's RGB, and we include top is equal to false, meaning that we don't want that head thing. We don't want it to be 1,000 classes. We want it to be 2. And we set the base model to trainable to be false because a neural network is about learning parameters. It has so many different layers, I think around 150, I could be wrong, of something that is already trained really well at classifying 1,000 different images. Now, the idea, and it turns out to be in applied math, what am I saying? It turns out to be when you actually apply this, it works out pretty much every time that if you have a convolutional neural network that is good at basically classifying any sort of images, then if you take mostly what's there, all of the parameters that have been learned, all you need to do is train the last layer, your new layer that we chopped off the end and put on our own 2 nodes at the end. We just need to learn that, and that is going to make a pretty good neural network. And so we freeze its layers for transfer learning, meaning we set the base model, all the exception stuff without the included top, to be false. Do not train this stuff. We do not want to touch it. In some cases, you may want to touch it a lot. In some cases, you might want to touch it a little bit. For our example, and we can actually get very good accuracy, is just do not touch it ever. Okay, so we're only going to end up training the end. So we have a base model, which is exception, which basically what it's going to do is download this exception model from Keras, wherever it's hosted. We're going to specify the input shape of a 299 by 299 by 3, a picture. We don't want the top, and we want it to be trainable as false. Okay, so that is that code there. Now, the tricky part here is that we are not done with this model. We have to append to this model. So I'm going to make a sequential model. So from that, I will do from Tensorflow.Keras.Models import sequential. So this is to basically append different layers onto each other. We can consider this as kind of a layer. It's just one big chunk of stuff that's going to happen. It is in charge of input and almost up to the end of the output. But what we do want to add is 2 things. We want to add a flatten and then our own dense, which is basically going to be the softmax. Okay, so when we do that, we would write it like this. We would do model is equal to sequential. So we're appending different layers on each other. Base model is what we have before. And so it's basically taking this list of different layers or stuff that we need to add. So it's going to take a base model, it's going to flatten it, meaning whatever dimension it was before, we want to make sure that it is just totally flattened. It is just a bunch of nodes. And then from that flattened thing, we can easily convert that into two dents by a activation of softmax, which is specifying that we want the probability of the first one to be the probability of that first class, and the probability of the second one to be the probability of that second class. I am optionally naming it the output layer. That may or may not come in handy. And of course, we want them to be two of them. All right, so we take our base model. We have a bunch of frozen layers, which are good at learning images or classifying images. We did not take the top. We added our own two at the end. That's all this code is doing. And we can output a model.summary, which shows you what the different layers of our model are doing. And it's going to take a little bit of time because it has a download exception. As you can see, it's downloading exception. And after that, it actually did quite well. So you can see huge parameter numbers. This thing outputs this 10 by 10 by 2048. We do not want that. We flatten that to be 204,800. And then we want to convert that into just a softmax of two things. And you can see we're still learning a bunch of parameters because we're converting this huge thing that exception is outputting into just two. There's actually a lot of connections there. It's not like you're just learning 4 parameters. You're learning all the combinations between these 204,000 and this thing. Hence, it's that pretty much times 2. Okay, so hopefully that makes sense. There's our model summary. That's transfer learning in a nutshell. If you want to learn more about, you could see a pictorial example of what I did for transfer learning as a video I'll link in the description below just for fun. All right, so now what we want to do is we have our model in Keras, but we have no way to connect that to the file structure. There's a bunch of different ways that people commonly do this. The easiest one for us is not to use the NumPy kind of X matrix training labels kind of way. It's because I set this up in our file structure so that we do not need to worry about any of that. And it allows us to do something which is a little bit creative, which I'll show you just by copying and pasting. This part is going to make pretty good sense. Okay, so firstly, I have to actually take an import. So here I need to import from tensorflow.keras.preprocessing.image, import image data generator. So this is this thing that's going to go over, it's a Keras thing, that's going to go over our file structure and say, okay, you're from this class, and I know that because of your file structure, so you have it set up so that you have cats and dogs, and so I know that this cats is the first class because alphabetically C comes before D, and so okay, everything in cats, these are class 1, everything in dogs, this is class 2. We don't need to worry about passing it the labels because I can figure that out from the alphabetized ordering of the folder structure. Okay, so we have an image data generator, and now how I'm going to set this thing up is first we're going to make a training data generator. So I set training data generator equal to the image data generator, so I'm instantiating one of these things. And now we're setting a pre-processing function equal to something that doesn't exist yet. All right, and that's because of the way I'm just organizing this lecture, is that we have to import this thing. Okay, sorry about that jump, I messed up a little bit here. We have to import this pre-processing function. So what we write is from TensorFlow, from TensorFlow.keras.application.exception preprocess input. So what a pre-processing function does is it says, okay, whatever input you are, I'm going to do something like standardizing or normalizing, some sort of scaling into the range of 0.1, negative 0.1, maybe something like that. For images, something commonly done is just dividing by the maximum value. The point is that we actually don't even care what this function is doing. So from TensorFlow.keras.application.exception, import preprocess input. That's how we'd write that. Let me just run that to make sure it works. Yes. Okay, so I know I still haven't explained everything that's going on here. Believe me, I will right now. So we have an image data generator where our preprocessing function, so what are we going to do first to this image? Exception by default doesn't do any preprocessing, so we need to add a preprocessing in here. And now, what is all this stuff? Well, there's this idea of data augmentation. And so we don't technically have to do this. We'd probably still get a pretty good accuracy without doing this. But what we do is say, okay, if you are an image that has a cat in it, well, if I zoom in a little bit on the cat, it's still a picture of a cat. And it turns out that we have so many pixels in a normal picture that this is totally okay, because look at the input that we're taking. We're taking in 299 pixels by 299 pixels by 3. If we have an image that is a bunch, like normal cameras are so many more pixels than this. So if you zoom in on this thing, you still have way more pixels than you need. And so we have a cat picture that's zoomed in. It's still a cat, so it's a valid picture that will help us in training. And it's still going to be shrunk down to the size that we need it later. We just do data augmentation stuff like, okay, sorry, this is rotation. So rotation range 20 degrees. If we rotate a cat 20 degrees, it's still a cat, and it'll help us in training. If we have another cat and we rotate it the other way 20 degrees, it'll still do that. Zoom, if we zoom in on a cat, still a cat. And if we flip one horizontally, is that still a cat? Yes, actually it is. These are some questions you'll have to ask for your specific data set. What does it make sense to data augment? You want to do as much as you can, because then you're artificially making a new data set, which is going to help you be much more accurate, because as you know, in deep learning, we are striving to have much more data. If you can do simple augmentations of the data to keep a valid label, meaning is this still a cat after transformation, and it's a different picture, it's probably something useful to do. You just have to ask what you want to do, and feel free to check the documentation. There's a bunch of other stuff. You could look into shearing and brightness and lighting changes. There's so many things you could do for images that will likely improve your accuracy. We'll see that it's actually very good for what we have, just like this. All right, so we have an image data generator, which is going to loop over our directory, and it's going to pre-process the image, and then it's going to possibly do some of these effects to transform it. This is valid in the training. It's not valid in the testing, because we don't want to test on images that we haven't really seen before. And it's also not really valid on our validation, because we also don't want to confirm that we're doing well on pictures that, it's helpful for training, but it's not really that helpful for, at least in my opinion, maybe someone else would do this. But in my opinion, I wouldn't want to confirm that I am accurately getting a cat picture that is an artificial cat picture. You absolutely could, but I think it's better just to confirm on real cat pictures and dog pictures. I'm only saying cats. Sorry, dogs. I'm leaving you out. I like cats slightly more, but dogs are really cute too. Leave a comment down below if you want to fight me on the cat versus dog conversation. I actually love them both. But yeah, so basically we're going to augment the training set a lot to get better training results and validation results, except we're not going to augment the validation and test results just because, really. Now, we are not done setting this training data generator up quite yet. There's another thing we have to copy, which is actually the training generator. I don't really like how Keras does this, but this is how you do it. Is you have this image data generator, and then you say dot flow from directory. Actually, I guess it's pretty nice. So we do dot flow from directory on that thing that we created, because we want to, as I said, we have this all set up in our file structure. So we just flow from the directory and say, okay, this is the structure. This is how you know what class is which, and you're good to go. So I'm going to pass it the training directory. So here, go there. The target size, we need to say it's going to be a 299 by 299 picture. Don't worry about the fact that we're excluding the 3 here. These are just, nitpicky things that are required sometimes. Color mode is RGB. We have an RGB picture. Batch size is something. I mean, I'm not going to get into the conversation of how to optimize your batch size. I chose 128. Class mode is categorical, meaning, okay, we're saying what is our file structure trying to do? It's saying, okay, these are cats, these are dogs. And shuffle is true. Now, shuffle is true because what it's meaning is if you didn't shuffle it, basically you have this file structure where you have a folder of a bunch of cats. Say that they're cats, the files are named 1 through 500, or if it's our training set 1 through 4,000, something like that. So if they are, that would mean each batch size of 128 is that batch, that 1 to 128, then it's 129 to whatever. It's a bunch of 128 partitions, the exact same ones. And it turns out for training a model, it's usually better to shuffle it a little bit so that we get, the first, and then the third, and then the 10th, and then the 12th, and then the 100th, and the 1000th in our first batch, and then something else in the second batch, and so on. So we're going to shuffle it equal to true. And we're going to do something very similar for the validation. We're also okay with doing most of these things. Sorry for the copying and pasting, but that's how coding goes, honestly. Validated gen is the same image data generator as before. Well, it's not the same one, but it's writing the same code. We still want to pre-process it, so we're passing it the same pre-processing function, but we're not going to do any of the data augmentation effects. So that's just our validated generator. And we're flowing from directory again, but we're passing it the validation directory. I don't know why it's looking like that. I'd rather it looks like this. Hopefully that works. And now target size is still 299, 299. Color mode is still RGB. Batch size is still 128. You could again adjust that. Maybe I should make that 64 because the validation is a lot smaller. And class mode is still categorical. Shuffle is still equal to be true. That way we're confirming on not just the same batch every time. We are mixing our different accuracies as we go. All right, so hopefully that makes sense. We now have it basically set up so that we can train our model. And I'll run that just to make sure. Yes, okay, so it does actually give us a really nice output, which is the training stuff found 8,000 images belonging to 2 classes, meaning about 4,000 each split, and 1,013 belonging to 2. Now let's do some math. We see 8,000 belonging to 2. We go up here, sorry, 8,005, and here we should have 8,007. Clearly there's some files in there that I think they included, the person that made this data set included some garbage files, which is totally fine. That happens when you upload data sets. There's also a chance that in pictures, Keras for whatever reason finds like a kind of a bug in the pictures, and it just doesn't like it. So it may ignore those as well. All right, so 1013 we compared to, it should be, this is in validation. So yes, that's right. It has all of those. 1013 right there. And yeah, that should be good. So now we're ready to basically fit the model right after we do some very little extra stuff here, which is compiling it. So I'm going to write model.compile. Optimizer is set to atom. It's just often what is done. Loss is categorical cross entropy, meaning, okay, we want to measure the fact if we're accurately saying whether this is a cat, if it is a cat, or if we're saying if it's a cat or that's a dog, and that's a dog, that's a bad thing. So that's how we're measuring our loss function. And the metrics we want to look at are really just accuracy. Makes a lot of sense. Now we're going to do something called a checkpoint. All right, so I'm going to need to import this checkpoint thing, which is right, sorry about this, from tensorflow.keras.callbacks. From tensorflow.keras.callbacks, import model checkpoint, which is just a way of saying it's constantly going to be saving our model as it iterates. So through each epoch, which is a run through the training set and also a check through the validation set, it's going to save some model, and it's only going to save it if it's best. That's what we want to do. So we want a folder, or we have that folder. It's in the model directory. We want to say, okay, save in this model directory, but only keep the best model. Now, best is in math. What do you mean by best? In this case, we mean how well you're doing on the validation set is what's actually important to us. Again, we can have 100% of the training set, and you could say that's our best model, but that's not relevant. We want to say, no, we trained on this set, and we're looking how well we did on this set. So we only want to save the ones doing really well on the validation set. And we would do that by importing this checkpoint thing. And I'm just going to copy over here, checkpoint. I'm also going to put that up a little bit. So checkpoint is equal to this model checkpoint thing. You can see it's from Keras. Is equal to model checkpoint of the model directory. Remember we defined that up here is model dir, this file here, or this not file, this string of the folder here. All right, so put it here. We want to save here. We want to monitor. So that's what I was saying. What is best? Well, best is validation accuracy. Verbose equals 1 is saying don't show us too much about the training process, but show us a little bit. Save best, or not training, I guess that would be the saving process. Save best only is equal to true. So only save the best one. And this just kind of goes with the save best is the mode we want to save the best model, all right? Or the highest accuracy. So if it's monitor is val accuracy, then we want max, meaning take the one with the highest accuracy. Okay, so we have that checkpoint, and now we are ready to fit the model. So how we fit the model is you'll be used to model.fit with an X and Y matrix. So check out how we can do it here. So we write model.fit train generator is this thing from before. So we pass it our X matrix, but except this is actually a thing that in Keras is going to automatically flow over our directories. So it's totally okay taking this generator. We want epochs to be, I don't know, this is one of those numbers that tough to say beforehand, maybe 2. Validation data is going to be the val generator. And the callbacks is going to be basically what do we do after we finish an epoch. We are going to call this checkpoint thing. And so it's going to say, it might save the best model. It'll definitely save the first one because it's going to be better than doing nothing, right? And verbose is 1 saying, okay, don't show us too much about the process. Let me run this on a GPU. Okay, so make sure accelerator is GPU. Turn on, it says I have 28 hours remaining. Hopefully you have more than that. If you're running out, then might want to look into doing this on Google Colab Pro, or I'm not sure if there's a Kaggle Pro. Someone let me know if there's a Kaggle Pro. It probably is. Actually, I would suspect, I'm going off topic, but I suspect if you buy Google Colab Pro, it's probably linked to Colab or to Kaggle. Okay, so we have a GPU now, and I think it still has I think this is still going to work. Model's not defined. No, it's not. Okay, so we actually need to run all of this again. So I am just going to go into run factory reset because I want to be able to do all of this stuff again, including the file structure, just to show you that it's all going to work from scratch. It says it's ready to use. I don't quite believe it yet. Yeah, I didn't believe it for a reason. Okay, so it's going to run there for a little second. If it doesn't take too long, I'm going to keep it here. Yes, okay, it's good. Show some of the files. Let's make our file structure there. Okay, now it's actually done. Make our folder structure and move our files. That'll take a little bit there. I'm getting messages. Sorry for the Facebook stuff, by the way. I should really mute that for next time. I'm not sure if you can hear it. You probably can a little bit. Okay, so moving all of that, it's taking a little bit of time. Again, if that takes too long, I'll cut this out, but if it's not too bad, then I'll keep it. 4006, there we go. There's going to be another big one here. Yeah, actually, I'm not going to cut it out. I'm also getting messages. Sorry about that. Just skip over to the end if you want to. There we go. Okay, it's almost done. All done. So now we're going to make our constants, make our model. It's going to have to download a exception again, which is going to take a little bit of time, but not too bad. There we go. And make our generators, define our checkpoint and compile, and then actually fit the model. All right, now this part, I'm not sure how long it's going to take. It probably will be pretty quick. I'm going to show you a little bit just in case you haven't done it before. I'll show you the results of at least the first epoch. It's going 2, 3, no, it's going to take a little bit of time. So I'm just going to talk about this right now, and then I'll skip to after the end of the epoch. So you can see basically how many batches we have here. We're doing batch 8 right now, and then out of 63, we're going to have that many total. So that's basically saying put all of these into main memory. I'm not actually sure how that works. But we're looking at these images right now of the training set, do some sort of math on that, some gradient descent using the atom optimizer, comparing that to the categorical cross entropy. And that is going to give us some sort of loss here. It's expected that I think just this epoch will take 1 minute and 45. And the accuracy is going up, as you see. This is training accuracy. So remember, this number you're seeing it right now is sort of indicative of how well our model is, but it's not important. Like, it's not actually something we would use to base any decisions off of. In general, we are trying to optimize this thing to get a lower accuracy, and higher accuracy, lower loss. So this should be going down, this should be going up, and you can see that it is. So this is good for now. I am going to skip over to at the end of the epoch. I will show you what's going on then. All right, so this epoch is just about to finish. So you can see we're on basically the last batch here, and 4 seconds left. Here we go. So we have so far a 92% accuracy on the training set. Now what it's going to do here is see, okay, well, we did all this stuff. Now let's see how well our model did on the validation set. For some reason, you can see, and I guess it's because we have less data in the validation set, is we have basically perfect on the validation set already. So you can see file accuracy improved. So it did save because it was obviously better than nothing. It improved from something that didn't exist into basically perfect. And we saved that to Kaggle/working/model. It outputs that for us already. Do we really need to run this again? I don't think so. So I'm just going to kill it. You can see it already saved it. So let's cancel that. We got a really long error that I'm going to hide. And yeah, so we trained our model. Now we're ready to test the model, which a number of ways is possible. Of course, if you're making an actual application, you'd probably want to do something like get an image from your phone or get an image from the computer webcam and upload it, or maybe get something from a URL on the web. And any sort of option is possible. Now, what I'm going to do is the simplest just for the point of this video, which is to use the test generation data we already have and just make a test generator that loops over that file structure the same way as this validation one does right here. It's basically the same thing. I am also going to add a little bit of code, which I'm not going to explain too much, that you might need if you are making an application that is more complicated. So something like taking a picture from a phone and converting that. I'm going to do that here. Now I am going to explain a little bit, but here's the gist. From TensorFlow, we're importing uint8, float32, and cast. This is just a data type kind of thing. Don't worry about it too much. Keras model. So we are going to change our model just a little bit. And we're going to need the input layer to do that as well. Okay, so we are basically changing the model so that it can be better at taking an image from, say, the web or something like that. All right, so why are we doing this? Or what are we doing? Input is 299 by 3. Data type is an integer. Okay, so it's taking an integer because if it's coming from the web, it is just an actual picture. And that is RGB values. They are integers. So it's okay. Here's our input. It's integers. Now we need to convert that to floats so that we do our pre-process. Okay, so note that now I'm doing the pre-processing. I am embedding this into the model, which is how it should properly be done, rather than by doing it through some sort of image generator thing. In an actual model, you want all of this to be separated. And so here, I'm going to now embed the pre-processing into the network, and then we're going to run our actual model. So all I'm doing here is saying, okay, I'm going to add a first layer, which is the input, which is an integer type, change it to float, pre-process it the same way as we did before, and then model is going to be where X is now the model of what it was before. So this is just the same model that we generated, same model that we created up here. I'm just adding these few layers beforehand and then saying X is equal to model of X. And this is just the Keras way of writing this kind of thing, is you have a layer and then you say, okay, here's this layer and this layer. If you were appending onto the previous layer, you would kind of write it as bracket X bracket or whatever you had it called. So that's called the functional API. You can look at that if you want. Basically, I'm just building a bunch of layers in rather than using a sequential model, which I probably could have done as well. Okay, so in the end, I'm making a runtime model, which is just the model I'm using for inference, to be the model that takes the inputs of that first layer and the outputs of X. Okay, and X is, after it's done all this stuff, it's going to basically just make the model that the same thing as sequential all the way through. It's going to do the input like this, the float like this, the pre-processing, the model that we already created, and then the runtime model. Okay, so that should work, and it does. Now, if that's our model, then the only thing we should have to do is save this thing. And we can do that very quickly by writing something like this, where I say save the model used for inference. Runtime model directory is constant, is going to be the path.join of model directory. So model directory, remember we specified that up here. We said that's going to be working model. So we have that, and then runtime. So that's just another folder saying, okay, let's put it in the runtime spot and let's save it there. Okay, so that's not going to be too long, but it'll be a little bit of time because it's an exception model and it's fairly complicated. And while we're running that, the only other thing, other than actually testing the model, we want to be able to load it back up. So here, load the model used for inference. We take from tensorflow.keras.models, we're going to import load model. It's just a function to take models. And then loaded model is load model which takes the file directory, which we have in that constant right here, and it just saved. So we should be able to have loaded model where we are grabbing from a file structure. We're saying, okay, put this model back into main memory, make it Keras, rather than like, so the point is that you would save this model in an actual application. Sometimes you would need to load that model, you would grab it, and then here it's back in main memory. We can use it right away. Now, this test generator is going to be basically the same as before. So right here, I'm going to do test data gen. Is that the same thing? Image data generator. And then test generator is this thing, dot flow from directory. This test stuff is still on our file system, so we're happy with that. Again, I'm not happy with how it's indenting that, so I'm just going to push it back a little bit, and that's not quite where I wanted it, but about there. Okay, hopefully that still works. So again, it's from test directory. We again specified that at the beginning. Target size 299, 299. Color mode is RGB. Batch size is again, maybe it should be something more like 64. Class mode is still categorical. Shuffle is false. We do not want to get confused in what we're testing because, as we'll see very shortly, we kind of want to know that it's alphabetical and how many pictures of each we have, because these generator things are nice in the sense of training, but in evaluation it gets a little bit complicated. That's why I'm only going to do something very simple to say how it's working. All right, so anyways, we're making a test generator where we can now run this thing and predict on it to see how well we did. To do that, we do need to make a prediction function. Okay, and in general, loaded model, or this Keras model, has a predict function. So we can say predict, and if we ask that, yes, it is a function. Now, what can we pass that? Well, watch, we can pass it test generator, and it will be very happy with that. But as we'll see, it's not quite what we want. So what we see is basically a matrix that has some amount of rows, I can check that, and some amount of columns. That column number is 2. We can actually see that one. So found 1010 images belonging to 2 classes. Okay, so it's an 1010 by 2 matrix where each of the entries, so one row, there's 1010 rows, the probability sum to 1, because we're saying, okay, this is the probability of it being the first class, which is going to be cat, because C becomes for D in the alphabet, and this is the probability of it being a dog. Now we can see that it is extremely confident that the first 3 are cats, and that makes sense because since I said shuffle is false, I am passing it a bunch of, basically a list of files where the first 500 or 6 or so, they are cats. So let's see, we can see that's very good. It's completely confident that it's a cat and that it's going to be the right answer. And then we can see near the end, the last 3, it's totally confident that the last 3 are dogs because, well, those are dogs. So now what I want to do is make this a little more readable for a human being such as ourselves. So let's write a function that basically converts this matrix into just a list where it's 1010 things or however many things we passed it. And it's got to take the argmax of these things, or well, it's going to take the maximum and then convert which one of that is into either the label cat or the label dog. So it needs to be if the bigger one of these two for each row, if the bigger one is 0, as in the index is 0, so the argmax of that row, if that's 0, then we got to return cat. And if the argmax is actually 1, then we got to return dog. So now let me show you what, well, if I import numpy as np, I'm not sure if we already have it, doesn't matter. And we do numpy.argmax of loaded model. So basically the same thing, loaded model.predict. And actually let's store that in variables because I might use that a couple of times. I'll say raw is in keeping the probabilities. Raw preds is this thing. And let me run that again. And actually, I want to output it again just so you can always see what that is. It's going to help us. I like to keep as many things outputted as we can without getting it too clustered. So we have raw preds is going to be this thing. And yes, it's the same thing as before. Now, if I give the numpy.argmax of raw preds, and then I pass it axis equals 1, which is basically saying do things on this particular axis, it means that when I take the length of this thing, that's how you know you got the axis right, is if it equals the length of this thing or the shape of this thing is the length that you actually want it to. So we wanted 1010 things, and so that's great. If we had, say, 2 there, if we had the number of 2, then we probably should have changed axis from 1 to 0 or 0 to 1 or whatever. Okay, so I'm saying I want the argmax of the predictions, and yes, on the right axis. Now I have 1010 things, which what it's actually producing is a bunch of indices. And you can see these are 0s correspond to cat, 1s correspond to dog. Now that we have the argmax of this thing is this 1010 length thing, where it has these 0s are cats and the 1s are dogs, I want to write a function that just converts those to its actual label. Okay, and it's very easy. But I want to do this in here. Okay, so I don't want to have the predictions like as a variable. I want to do all that computation in our prediction function. So for that, we're going to need a model, and we're going to need to pass the data in, and it's going to be, so model we're going to assume is the loaded model, so that one in memory right now, and the generator we're going to assume is the test generator. All right, there's better ways to write that function, but I think that's totally fine. So here, when we call predict, and all we're going to do is call model.predict. Okay, so that gets model.predict on the generator. That is going to get that prediction as above. That is the same thing as a matrix. So what I want to say is basically the indices, or the, let's say, max indices, is the numpy.argmax of that thing on axis equals 1. Okay, it's the same thing I showed you before, and now it's just putting this thing into a variable in this function. All right, so now that we have that, basically we just need to convert that into cat or dog. So the easiest way to do this is just to return, if this is a numpy array, then actually there's a function where you can say, and I'll show you, it's called .toList. So if I have a numpy.array of 1, 2, 3, and this is toList, let's just convert that to a list, because you could do this all in NumPy, but I would rather just kind of get this into normal Python code. So this is the same thing, but it's not going to have array here because it's just a Python list. And then what I want to return is this list. I'm using the comprehension syntax. Makes building lists very easily. I want to return cat if x, or x is going to be each of these indices, and actually I'll use I because of that. Cat if I is equal to 0. Otherwise, I want to return dog, because it means it must be 1. That's all it could be. If you had more classes, then if you had way more classes, there's definitely a more sophisticated way to write this function so that you can automate this process of kind of saying what label it is. But for now, with 2 classes, this is just fine. So let's return that list. And then if I just call predict, then it should work by itself because it doesn't have any required arguments. So it's going to run this calculation and fail. And it's failing because, what am I doing? Max indices is numpy.argmax of model.predict generator on axis equals 1. And then convert that to a list. That should be fine. Return the list of cat if I equals 1. Yes, so this should be for I in max indices. Sorry about that. So we're saying iterating over this thing and translating it. That should work now. Yep, so it's got a bunch of cats. And again, let's store this in a variable saying basically predicted labels is equal to predict. And let's ask the length of predicted labels. Okay, and sorry about it being a little bit slow right now. You can obviously skip 5 seconds here and there to get through this stuff. So 1010, there we go, should be good. So now we have the label corresponding to the generator for each of the images, whether it thinks that image in order was a cat or a dog. Now, the true labels are easy to gather. You could probably get it from the test generator itself, but I'm not going to do that. We're going to do something that it's going to be 99% accurate, if not 100. So basically our test generator, you can see here, it found 1,010 images belonging to 2 classes. We know, actually, it should be right here. Sorry, I'm going back and forth. This isn't actually, what I was about to say isn't that accurate. So this is actually quite fine that we can do. Sorry about scrolling around so much. So we found 1,010 images belonging to 2 classes. We know, yes, there might be a very slight error in one of the images or maybe in a couple of the files, but in general, it's going to be very, very close to the first 505 are cats and the second 505 are dogs. So it's let's just say, and maybe it's not exactly true, but it's very, very, very close to true, that the true labels is going to be equal to the list of cat for I in range 505. So that'll produce 505 things, all being cat. And then it's going to be the same thing, but dog. Okay, these really are the true labels. It's a little bit of a hacky way to do this, but this is just fine. And let's confirm that actually, sure, let's just output that for now. It should be nice and quick. So a bunch of them are cats, and then when we go down, we see a bunch of dogs. And let's confirm just again that the length of true labels matches. Okay, so then all we need to do is we have our predicted labels and we have our true labels, at least close enough, and then we just need to see where it differs. So the accuracy is really going to just be, and I don't even need to write sure, we'll write a function for it just for fun, which is going to be define get accuracy, and we'll ask for predicted labels. And this might not be the most optimized way, but it's just fine. Predicted labels and true labels, which says, let's say correct amount is equal to 0. And then for x, we can iterate through both lists at the same time with zip if you haven't seen this. So basically, it's just for predicted label and true label in the zip of predicted labels, true labels. Okay, so all that's doing is iterating through both of these at the same time, where each time in the loop, this is a member of that, and this is a member of that in the right order. So we can compare them, and we can say if p label is equal to the t label, that means it's the correct guess. And so our correct amount should go up by 1. If not, that's fine, and we'll do that all the way. And then all we need to do to produce the actual accuracy is return correct amount, so however many we got right, divided by the number of predictions, or equivalently the number of labels there are. It's just the length here. So we need how many things there actually are to produce our average. And so get accuracy, which actually I will write this, is equal to this thing by default. And true labels is going to be this actual true labels by default. Get accuracy should then not need anything. It's just going to output that we got basically everything right, maybe one wrong, maybe that's just because of the error. We have amazing accuracy. So that's the end of the video. I hope you liked it. If you got this far, please give me a like. And if you're not subscribed already, I really hope you subscribe to the channel. It'd mean a lot. So thanks so much for watching. I'll see you next time.